All right, this problem says, if a hoop having mass m and radius r is allowed to roll down a ramp inclined at an angle theta above the horizontal, what is the acceleration of the hoop in terms of g and theta? So let's get our ramp. Like so, and our hoop. Now, first thing that we need to do, let's put our forces on here. So we have a force of gravity acting downward. This is Fg equal to mg. We have a normal force acting perpendicular to the ramp, and because this is a hoop, it is rolling. There is also friction between the surface of the ramp and the hoop, and the ramp is inclined at angle theta. From there, I'm going to break up my gravitational vector into a parallel and perpendicular component. So this is Fg perpendicular, which is mg cosine of theta, because this angle here is theta. And this is Fg parallel, which is mg sine of theta. Keep in mind, guys, also that the object is rotating, okay, with some angular speed omega, and is moving with some translational speed v. Now, in order to start with acceleration, I'm going to first write out Newton's second law. F net equals ma. We are looking along the ramp, so mg sine theta will be positive because direction of motion is going to be positive, friction is going to be negative. So I have mg sine of theta minus friction equals ma. Step 2. We'll write out the torque net equals I alpha. This is Newton's second law, just rewritten for rotating objects. And the goal here, in order to get acceleration, is to marry these two equations together. So if I look at my hoop, like so, and we kind of blow our picture up here to try to figure out the torques, we have gravity. Here is the ramp. We have the normal force. And we have friction here. Now, if we look at the torques caused by each of these forces, so if I look at torque due to normal, torque due to gravity, and torque due to friction, and I write out these torques, torque is defined as R cross F, or the magnitude of F times the magnitude of R times the sine of theta, where theta is the angle between R and F. Now, with a normal force, the force is applied here. So R is the distance between the axis of rotation, which is the center of my hoop, and where the force is applied. So this is R. And you will notice that the angle between R and the normal force is 180 degrees. Sine of 90 is 180. So we are left with the torque due to the normal force as 0. Now, for force of gravity, in this case, we have force of gravity times R times sine of theta. But again, R is the distance between the axis of rotation and where the force is applied, and gravity is always drawn from the center of mass, which is on the axis of rotation. So for gravity, R is 0, so that is resulting in a 0 torque. Now, for friction, you will note, guys, that friction acts up the ramp, and the distance from the axis of rotation and where the force is applied is r, and there is an angle that does not make sine 0, and that angle is 90 degrees. So I'm left with friction times the radius times sine of 90, which just gives me r friction. Plugging that in for torque net. Note, guys, if I sum all of these torques, just a sum of all the individual torques, I just get our friction here. Let's plug that in for torque net. So we have R friction equals I. I'm looking for acceleration, so I'm going to rewrite alpha as A divided by R. So friction becomes IA over R squared. From there, I will take that value and I will plug it into my Newton's second law equation. So in doing so, I have mg sine of theta minus IA over R squared equals ma. Rearranging, I get I A over R squared plus ma equals mg sine of theta. I can factor out ma on the left, and I get IA over R squared. Excuse me, I get I over m R squared plus 1 equals mg sine of theta. From there, mass will drop out, so I'm left with acceleration is g sine of theta over I over mr squared plus 1. Now, we are looking specific to the situation where we're dealing with a hoop, and I of a hoop is equal to mr squared, which I've derived for you in a previous video. So plugging this value in for I here, you'll notice the mr squareds will cancel, giving us 1. And so I get acceleration as g sine of theta over 2 for a hoop down a ramp. I hope this was helpful, guys. Thanks.